Welcome back, everyone. So today on The Explainer, we're embarking on this really incredible journey. We're going to explore the totally hidden universe of invisible waves that literally surrounds us every single second. And we'll connect that physics to the everyday magic of our colorful skies. If you love understanding exactly how the world works, well, you're definitely in the right place.
I want you to just think about this for a second. Have you ever wondered why danger signals, like stop signs and tail lights, why are they universally red? Or how about this? Why, when an astronaut leaves Earth's atmosphere, does the sky go from a brilliant blue to completely pitch black? Well, it's not just a coincidence. The physics of light actually holds the absolute, verifiable answers to these everyday mysteries.
Okay, so here's our roadmap for today's explainer. First, we'll look at the magic of prisms. 2, the electromagnetic spectrum. 3, radiation in everyday life. 4, the science of scattering. And finally, number 5, the colors of the sky.
Let's jump right into section 1, the magic of prisms, splitting the light.
To really understand the massive sky above us, we actually need to start by looking at something super simple, just a small piece of glass. The foundational concept we need to grasp here is called dispersion. By definition, dispersion is basically the phenomenon of splitting white light by a prism into its constituent colors. So the big takeaway here is that what we perceive as just plain old white light isn't actually just one color. It's this rich, incredibly complex mixture of many different wavelengths, all packed together.
You've probably heard of Sir Isaac Newton's famous prism experiment, right? He basically allowed a single beam of white light from the sun to enter a completely dark room and pass right through a glass prism onto a screen. And what emerged was just this beautiful spectrum of colors: violet, indigo, blue, green, yellow, orange, and red, which, is easily remembered by the acronym VIBGYOR. Newton figured out that the prism actually isn't creating these colors at all. The glass just separates the hidden colors that were already hiding there inside the white light.
So, the really crucial question is, why do they separate? Well, it all comes down to their physical properties. See, light of different colors travels at the exact same speed in a vacuum, or out in the air. But the moment it hits a dense medium like glass, the rules change. Violet light, which happens to have the absolutely shortest wavelength, ends up traveling with the lowest speed inside the glass. Because it slows down so much, it gets bent or deviated the most. Red light, on the flip side, has the longest visible wavelength. It cruises through the glass a lot faster, so it deviates the least. And that right there, that difference in speed and bending, is exactly what pulls the white light apart into a rainbow.
Moving on to section 2, the electromagnetic spectrum, the invisible universe.
Okay, so if we zoom out from that tiny visible rainbow, we uncover this massive, completely hidden universe of light that is literally constantly flowing all around you. What's truly staggering here is the sheer scale of what we can't see. There's this tiny little band right in the middle labeled visible, and that is everything our human eyes can detect, just from violet to red. But this spectrum extends massively on either side. Way beyond the red extreme, we have these huge invisible bands of infrared radiations, microwaves and radio waves. And then on the other end, just past violet, we've got ultraviolet rays, X-rays, and gamma rays. This whole giant continuum, that's the electromagnetic spectrum.
Now, despite having wildly different wavelengths, we're talking gamma rays the size of a single atom, all the way up to radio waves that are meters long, they all actually share some strict fundamental rules. First off, none of these waves need a material medium to travel. They can just fly right through the absolute vacuum of space. And in that vacuum, they all travel at the ultimate cosmic speed limit, 3 × 10⁸ meters per second. Plus, they all reflect and refract, they're all transverse waves, and really interestingly, they aren't deflected by electric or magnetic fields at all.
Okay, section 3, radiation in everyday life, harnessing the invisible. Even though our eyes are completely blind to almost this entire spectrum, human ingenuity has figured out how to harness these invisible waves to basically power our modern world. Let's just walk through a few of these. X-rays, which are generated by bombarding heavy metal targets with electrons, are incredibly penetrating. They pass right through human flesh but get stopped by bone, which is exactly what makes them so perfect for medical scans. Then you've got ultraviolet light coming from the sun or arc lamps. It's chemically active, and we use it practically all the time to sterilize surgical equipment. Now, infrared radiation, that's basically just heat. Anything hot emits it, which lets us use it for things like night photography and, yep, even the remote control for your TV. And microwaves, generated by electronic oscillators, they are uniquely suited for both satellite communication and, heating up your frozen dinner. So really, we're just constantly surfing this massive ocean of invisible light.
Let's keep moving to section 4, the science of scattering, Light meets the atmosphere.
So, bringing all this knowledge of wavelengths back down to Earth, we finally hit our central question. Why exactly is the sky blue, but sunsets burn this brilliant red? I mean, you look at it every single day, but how does it actually work? Well, it turns out the mathematical properties of the light waves we just talked about, they hold the secret key to this whole thing.
It all starts with this process called scattering. See, when sunlight enters Earth's atmosphere, it doesn't just travel in a perfectly straight, uninterrupted line straight to our eyes. Actually, it interacts with all the incredibly tiny dust particles and air molecules floating around up there in our atmosphere. Scattering is simply the process where these particles absorb the incoming light energy and then almost instantly re-emit it, basically just spreading it out in all different directions.
But here is the magnificent catch, which was discovered by a scientist named Lord Rayleigh. The air molecules don't actually scatter all colors equally. The rule is that the intensity of scattered light is inversely proportional to the fourth power of the wavelength. Okay, I know that sounds super complicated, but here's what it means in plain English. The shorter the wavelength, the vastly more it gets scattered. Period. Remember our prism from earlier? Violet and blue light have the absolute shortest visible wavelengths. Because of that, they get scattered across the sky nearly 16 times more than the long wavelengths of red light do.
And that brings us to our grand finale, Section 5, Colors of the Sky.
Let's actually take Rayleigh's law and use it to paint the sky. Think about where you are standing on Earth. Now, at noon, the sun is directly overhead, right? So the light is traveling a relatively short, direct distance through the atmosphere to reach your eyes. But during a sunrise or a sunset, the sun drops way down near the horizon. Suddenly, that sunlight has to travel through this massive, thick, horizontal slice of the Earth's atmosphere before it ever reaches you.
So let's just walk through what happens step by step. Step 1, during a sunset, the light is making its absolute longest possible journey through our atmosphere. Step 2, because of that Rayleigh scattering we talked about, the shorter wavelengths, all those blues and violets, they are violently scattered away in every direction very, very early on in that long journey. They just get completely lost from the direct beam of light. So step 3, what's actually left? Only the really resilient, long wavelengths. The red and orange light scatters the least, so it successfully survives that epic atmospheric journey right into our eyes. And that is exactly what renders the sun and the horizon in that brilliant blazing red.
Now let's circle back to that question from the very beginning about space. Why exactly is the sky black for astronauts? Well, because to have a blue sky in the first place, you desperately need atmosphere particles to catch and scatter that blue light down to your eye. Out in the vacuum of space, or say on the moon, there's no atmosphere. There are literally no air molecules. With zero particles around to scatter the sunlight, the sky is completely devoid of scattered color. So it just appears totally pitch black, even when the sun is blazing right at you.
And what about those danger signals we mentioned? Turns out, making them red isn't just some random cultural choice. It's actually optimal physics. Because red light has the longest visible wavelength, remember, it scatters the least. So when you're driving in really heavy fog or rain or just looking way down a long distant road, the blue and green light just gets completely scattered away by all the water droplets and dust. But the red light? It slices straight through all that mess, remaining bright and clearly visible from a massive distance. We literally use the physics of minimal scattering to keep ourselves safe on the roads. How cool is that?
Man, we have covered some absolutely incredible ground today. Think about it. We are basically living right at the bottom of this vast ocean of light, and most of it is entirely invisible to us. Yet it's quietly dictating our technology, keeping us safe, and literally painting the colors of the sky right above our heads. I want to leave you with this one thought to ponder. How completely different might our perception of reality be if, tomorrow, our eyes could suddenly detect the entire electromagnetic spectrum? It's pretty wild to think about. Until next time, keep looking up and keep questioning the physics of the world around you.